This is part 5 of Unit M and N. This is the nervous impulse. And if you watched one of the screencasts on the nervous system, I would recommend this one. So the question in this lecture is to understand how a nerve impulse travels from one point in the body along a neuron to the end of that neuron. So essentially, we're trying to understand how, when I touch my hot coffee cup, does that message run up my arm, a neuron, and through my spine, and finally get to my brain. So when I'm touching my hot coffee cup, right, it's going to receive a nerve impulse for touch. And so how does it get there? The big idea in this lecture is that we're talking about how the message travels along one neuron. We're not talking between neurons, so remember the order of parts in a neuron: dendrite, cell body, axon. How does it travel from the dendrite through the cell body and then get to the axon? That is the big idea, and that is worth making sure you understand. We're talking about one neuron, not many. The message is going to be an electrical chemical message, not like electricity in a wire where electrons get excited, but we are going to have a charge, but it's going to be generated by ions, so particles that have a charge, and in this case it's going to be sodium Na+ and potassium K+. It's going to be an all or nothing, meaning it either happens or it doesn't. There's no in between in a nerve impulse. A nerve will either carry the message or it won't. Some key vocabulary. So again, if vocabulary gets you down, this I would recommend pausing here. Sodium and potassium gates. This goes back to Unit G. Gates are going to be passive transport, no ATP. It's going to be facilitated transport. Sodium and potassium pumps. Pumps are going to be talking about active transport requiring ATP, and so this goes back to Unit G, and if you weren't here for Unit G, then that would be something you would want to attend to: active transport and passive. And my little picture, the dancing banana with a salt shaker shaking on top of him, the salty banana, right? Sodium, Na, potassium in our banana, salty banana. So the pictures, using our eyeballs to do some eyeball work that we are going to need to be able to recognize, we're talking about a pump. A pump is going to be something that uses ATP to move molecules against the gradient. We're going to be talking about two gates or channels: potassium, the banana, and the salty, sodium channel or gate, and potassium channel or gate, and these are going to be for facilitated. Again, if you don't know what facilitated is, it is well worth your while to pause here and figure that out. Okay, so the story has 3 parts. Resting potential, so just like the man and his little kitty cat, the impulse is not occurring, resting. Action potential is going to have 2 parts: depolarization and repolarization. So action, right, when the director yells action, this is when the impulse is occurring. At the end of the impulse, then the neuron is going to have to recover, and we call this the refractory period or recovery. And just like Eminem had to recover from drug abuse, right, the neuron has to recover from carrying an impulse before it can carry a new one. So an analogy, I really like analogies. When we're talking about the impulse, thinking about dominoes might help. We have to set up the dominoes before they can fall. And when they fall not all together. They don't all fall over simultaneously. They fall one by one by one by one. And this is going to be how the impulse happens. The whole neuron doesn't carry the impulse at one time. The neuron is going to pass the impulse along the length of it, like dominoes falling. So let's go into the story. Resting potential. The inside of the neuron, remember we're talking about a cell. A neuron is a cell. The inside is going to be negative 65 millivolts. Little m, big V for volts, is going to be overall negative. The outside is going to be overall positive. So this is this black line here on both sides is representing the cell membrane, and this is the inside of it, and this is the outside of it. How does this happen? At resting potential, there's a high concentration of sodium inside, and there's a high concentration of potassium, here's the cell membrane, on the inside. But you would say, well, sodium is positive and potassium's positive. How does it end up negative? Well, there are large negative ions that are maintained. They're too large to sneak out, and this is what gives the inside an overall negative personality. So my memory jogger, when you go to sleep, when resting, you're in with your kin. So at resting, K is in for kin. Resting potential is maintained by sodium and potassium pumps. This is active transport, and you can watch the little graphic here. Is it going to run? Maybe not. That sodium is going to be pumped out, and potassium is going to be pumped in against the gradient, and this is going to require ATP. And I don't know why it didn't run. Anyways, two parts to the action potential. Depolarization, part 1. Repolarization, part 2. Depolarization. Sodium gates open. Sodium gates. Gates means, or channels, means passive transport, no ATP. So the sodium that was outside of the cell is now going to diffuse in. So this is passive transport, no ATP energy needed. Depolarization is going to cause the polarity on the inside to change from negative to positive. And we're seeing this graph, it goes up to 40, positive 40. It's going to change. Whoops-a-doozles. Sorry, go back. Repolarization, no. Repolarization, there we are. So this is going to change. No, sorry, I apologize. That went crazy too fast. It's going to go up to positive 40 millivolts. Okay, now we can repolarization. So once the neuron has reached positive 40 on the inside, the sodium gates will close and potassium gates will open, and now potassium is going to move out. So sodium channels are now closed, and this is the cell interior, so this is going to move out. Repolarization, the inside of the cell is going to return to negative. So we went up to positive 40, and now we're going back down to negative 65. So it's returning, it's repolarizing. Recovery then, and I don't know why my little pump, oh there, it's going to go here. My little pumps turn back on. So sodium is going to be pumped out, and it's actually a ratio of 3 sodiums for every 2 potassium. So 3 sodiums go out, 2 potassiums come in, and this is going to restore ion distribution of resting. So recovery is going back to the same ion distribution of resting. We're almost out of time. The graph is important to look at and understand, tell the story through the graph. So resting, just like when you're lying down, it's going to be horizontal. When the neuron receives a stimulus, it has to reach a certain threshold. Once it reaches the threshold, it is all or nothing. So it will depolarize, or we can call this the upswing, to positive 40. Sodium gates at the top will close. The potassium gates open, and this repolarizes the inside of the cell. There is a brief recovery period where it hyperpolarizes, and this is when the sodium potassium pumps turn on again to restore the ion distribution. We will talk about this in class, look at this in class, but we should have an idea of that as we move down the length of the neuron, what we're looking for. So sodium entering is always going to lead the impulse. Right behind it, potassium exiting. So this is the depolarizing, this is the repolarizing right behind it. And we're out of time. Hope that helped.